All right, hello class. Welcome to the second part of this limits at infinity lesson, where we're going to take what we talked about last time and actually apply it. And it turns out there's a very nice little algebraic way to find limits at infinity. And it's essentially a factoring method. And there's some other complications that can arise. Here are some things to sort of show us where we're at the moment and how we're going to use it as we go forward. All right, some takeaways from part one. Now, we might not have explicitly said some of these things, but they do come about from the things that we've discussed. Essentially, if you have like an infinity plus an infinity, that's of course going to go to infinity. There's no issues there. Okay, and an infinity times an infinity, that's going to go to an infinity. Okay, there's really no issues there. What is always the question? Okay, and these are what you can consider the indeterminate forms. Okay, which would be infinity minus infinity. Right, so that's the first one that we sort of dealt with last time, because this could be infinity. It could be, say, a number like an L, or it just might not even exist depending on what we're talking about. It could be a minus infinity, right? So to give an example, if you had x minus x to the fifth, we know, and we're talking about the limit as x goes to, let's say, positive infinity, this will go to negative infinity because it's that negative x to the fifth that takes over. However, on the other hand, if we had the limit as x goes to infinity of x to the sixth minus x squared, well, this is going to positive infinity. Okay? And on the other hand, if we had the limit as x goes to infinity of, let's say, x squared minus 2x squared, that's not something we would usually look at. But, you know, that is going to end up being the limit as x goes to infinity of negative x squared. So that will be negative infinity. Or if we have the limit as x goes to infinity of, let's just say, x minus x, right? That's going to come out to be 0, because at every step we get an x minus x. So there are a lot of ways we can get an infinity minus infinity. Okay. Then the other indeterminate form is infinity over infinity. Okay, and that similarly can be anything. That could end up being infinity. It could end up being some number. Okay, so this really comes down to which piece is going to infinity faster. Okay, so for example here, x to the fifth goes to infinity way faster than x does, so it takes over and gets us down to negative infinity. However, x to the sixth goes to infinity faster than x squared, so it's the one that takes over and leads us to positive infinity. Okay? So that's really what it comes down to, is which piece goes to infinity the fastest. Okay, and our last little piece of information that we need, it's that a constant over infinity goes to 0. Okay, and this we can use to do just about everything. All right, that doesn't sound like it's possible, but it really comes down to what I call a very particular way of factoring. All right, I'm going to call this funky factoring. It's something you may not have thought about before, because you probably haven't had to use it before. But funky factoring could be something like this. If you have, say, 2x plus 3, okay, and I want to factor an x out of this. Okay, well normally what you would be told, or what you would say, is that you can't, because the only piece with an x is here. However, it turns out you can factor an x out, provided if you do it, you divide everything by x. All right, so factoring is essentially dividing out the item. For example, if let's say I want to factor out an x. I know I can factor it out from here, but I want to factor out an x from here. Okay, so what I'm going to do is just say, write the x on the outside, and then put 2x over x plus 3 over x. So what ends up happening is we get x times 2 plus 3 over x. Now, how do we know this actually works? Well, if you distribute that x back through, you end up with 2x plus 3x times x, which is 2x plus 3. That is right where we started. Okay, it turns out that factoring is just a form of division, right? Because here, say I have 2x squared plus 8x. Normally we would factor out a 2x because they both share a 2 and an x. So if we do that, if I instead take everything in here and divide it by what I'm factoring by, this is just to show what's going on, okay, with an example we've seen before. In this case, the 2's cancel and the x cancels with one of these, and here the 2 cancels with the 8 and leaves a 4, and the x's cancel. And so we're left with the 2x times x plus 4. And that's what we would have gotten if we just factored like normal. So factoring is technically dividing everything. Okay. Another thing you could think is multiplying by a funky version of 1. Okay. So by multiplying by a funky version of 1, for example, if we're back here with the 2x plus 3 again, right, and let's say I want an x on the outside, so I multiply by x over x. Right, that's a funky version of 1 because anything over itself is 1, provided that x is not 0. Right, that's something we do need to be careful about. All right, but now if I rewrite this as, let's say, x times 1 over x, okay, times 2x plus 3, and then I distribute this 1 over x through, okay, we're going to end up with x times 2x over x plus 3 over x. Here the x's cancel, and we get x times 2 plus 3 over x. Okay? So this is all to say that you can factor things out like this, provided you just divide by it. All right. Well, how's that useful? Well, I'll show you. All right, let's say we want to find the limit as x goes to infinity of negative 3 times x to the 7th minus 5x to the 5th plus 3x to the 4th minus 10. Now, we've already talked about how we would do this. Normally, we would just say, okay, that's going to be the limit as x goes to infinity of the leading term, right, the negative 3x to the 7th. Okay, and then that's going to go to negative infinity. All right. However, I want to show you that we can also use the funky factoring, right? Because this will be, let me use a different color here. So this will be the limit as x goes to infinity. If I use the funky factoring, okay, I'm going to take out, let's take out just x to the 7th. Right? I have x to the 7th, and I'm going to divide everything here by x to the 7th. So it would be negative 3 x to the 7th over x to the 7th minus 5x to the 5th over x to the 7th plus 3x to the 4th over x to the 7th minus 10 over x to the 7th Okay, and you might think that I've just made that way worse. However, right, these x to the 7ths just cancel, so I get -3 minus, and these cancel, but they leave some x's in the denominator. So this will be -5 over, you should only have x squared left over. Okay, here, x to the 4th over x to the 7th, that should be 3 over x cubed. And this, well, that just stays as 10 over x to the 7th. Now, here's the thing, here's the part where we're going to use the constant over infinity goes to 0, because each one of these pieces now are going to go to infinity in the denominator. So here we have 5 over infinity, 3 over infinity, 10 over infinity. So these are all going to go to 0, meaning that this whole limit now becomes a limit as x goes to infinity of x to the 7th times, well, all that's left is -3. So in other words, this is the limit as x goes to infinity of -3 x to the 7th, which is just going to be -infinity. Okay, so we got the same thing here from what we already talked about, viewing it from the graph. So I'm not suggesting we do this every time. I'm just suggesting that algebra has verified what we have already sort of established graphically in part 1. All right, now this is going to be way more useful in situations like this, where we have an infinity over infinity case, or like infinity minus infinity, any infinity and plus infinity. Basically, things with fractions are going to be way easier to employ this sort of technique this way. So what I'm going to do is, whenever I have an infinite limit with fractions like this, I'm going to do the same thing I just did. I'm going to do a funky division, or a funky factoring. Okay, so this will be the limit as x goes to infinity of, in the top, let's just take out x to the 5th. All right, so we'll be left with 40 plus x squared over x to the 5th. So notice I kind of skipped a step here, because 40 x to the 5th divided by x to the 5th will just be 40. All right, and then here I'll factor out the highest power. So basically I'm factoring out the highest power, right, in the top and the bottom. All right, so here I'll be left with 16 minus 2x over x to the 4th. All right, so I should specify here, right, so we're going to factor out the highest powers of x. That's what makes it funky, right? That's what makes it funky factoring, is we're used to factoring out the lowest power of x, right? But now we're factoring out the highest power. And the reason is because I want those fractions. This is one of those few times where you want fractions to be introduced, because now, well, x to the 4th on the bottom will cancel with the x to the 5th and just leave an x on the top. So we have an x times 40 plus x squared over x to the 5th, and that's going to be 1 over x cubed all over. And then down here we're just left with 16 minus 2x over x to the 4th will be 2 over x cubed. And as x goes to infinity, these guys are going to go to 0. Okay, so this is essentially going to be the limit as x goes to infinity of 40x over 16. All right, and then that is the limit as x goes to infinity of 40 over 16. That's going to be 5 halves? Yeah, 5 halves x. Well, x goes to infinity as x goes to infinity. This is a positive coefficient, so this is just going to be infinity. Okay, some things to note here. We don't have to do this every time. However, I do want to specify that is what's going on behind the scenes when we learn the more shortcut version of this. Of course, that's what we're going to really focus on, is the shortcut. Okay, that whole higher powers of x thing. If we instead employ the highest powers of x, okay, if we instead employ that leading terms idea that we talked about last time and do this same limit, okay, so this same limit, and now if I just think about the leading terms of the top and the bottom, so this will be the limit as x goes to infinity of just be 40x to the fifth, that's the leading term of the top, over 16x to the fourth, that's the leading term of the bottom. That's going to simplify down to just be the limit as x goes to infinity of 5x over 2, the same thing we got here, which is going to go to infinity. That is a way quicker way to do it, of course, but behind the scenes is all of this incorporating the constant over infinity case as we go along. Okay, but this is just taking the leading term of the top and bottom. Okay, and then simplifying. Okay. Now the thing to note here is the piece, like this of course is an infinity over infinity case, but the top is x to the fifth, the bottom is x to the fourth. It's the top goes to infinity faster than the bottom. So it's the top that takes the whole thing to infinity. Right? So infinity over infinity, this is faster on the top, so it's going to take the whole thing to infinity. Okay. Let's look at another example. All right, for this example, let's take the limit as x goes to infinity of 14x cubed plus 3x squared minus 2x all over 21x cubed plus x squared plus 1. Okay, well, since it's a limit at infinity, so the thing to remember about limits at infinity are basically leading terms and that a constant over infinity is 0. Okay, so we're going to take the leading terms. So the highest power of x is going to be x cubed, so this will be 14x cubed. And the highest power of x, or the leading term in the denominator, is 21x cubed. Oh, so the x cubes cancel, and we can take 7 out of both of these to get 2/3, and there we go. Oh, so in this case, the top and the bottom go to infinity at the same speed. All right, so top and the bottom go to infinity at the same speed, meaning that they cancel each other out when they're dividing, and then we're left with just the leading coefficients, okay, and then the fraction that they create, okay, because all these guys are just going to disappear, and then we're left with just what's in front of the leading terms, because it all cancels out. All right, let's look at another example. Okay, here's another example. Let's say we're looking at the limit as x goes to negative infinity of x to the fourth plus 7 all over x to the fifth plus x squared minus x. So, once again, we're just going to take the leading terms. So we'll have the limit as x goes to negative infinity of just x to the fourth over x to the fifth, and then we'll simplify. We'll have the limit as x goes to negative infinity of, let me make that look a little nicer. Well, x to the fourth over x to the fifth, that'll be 1 over x. And then what we've done is we've taken what is essentially infinity over infinity and made it a constant over infinity, and specifically a constant over negative infinity, which is just going to be 0. Okay? So in this case, we have an infinity over infinity, and it's the bottom goes to infinity faster than the top, right? Because the top is x to the fourth, the bottom is x to the fifth. All right, when that happens, infinity over a faster infinity, right? This infinity takes over, okay, and drags the function down to 0. Okay? Now these things that we've seen so far are actually always going to happen. However, if you don't want to just memorize that, you can always work through it like we've just done, but that is the pattern that we will always see. All right, so as I've said before, the infinity over infinity case depends on which piece goes to infinity faster. Okay, so if we have infinity over infinity, right, we have a couple of possibilities here. This will go to infinity, plus or minus, of course, if the top goes to infinity faster. Okay. On the other hand, infinity over infinity will get shrunken down to 0 if it's the bottom goes to infinity faster. Okay, so what essentially happens is if the top is going to infinity faster, it eventually is acting like, let me say acts, write it over here, acts like an infinity over a constant, because eventually the top infinity just totally outclasses what's happening on the bottom. It might as well be a constant. And down here, if the bottom is faster, it's going to act like a constant over infinity, which is 0. Okay. However, if they match, right, we're going to go to some sort of fraction a over b if the top and bottom go to infinity at the same rate. Okay, they essentially cancel, right? So I'll say essentially cancel. All right. Now this is always going to be true no matter what it is we're talking about. But for the time being, it's mostly like powers of x and whatnot. Okay. However, this isn't always super easy to just look at. Okay, so what I mean by that, it's not always easy to just look at it and know, or it's not always, that easy as just looking at it. But like for examples like this, maybe it is. Like the limit as x goes to infinity of x to the fifth plus 10 over x squared plus 1. The top is definitely going to infinity faster. Okay, for this one over here, x squared plus 1 over x to the fifth plus 10, as x goes to infinity, it's definitely the denominator that goes to infinity faster, so that goes to 0. And here, the highest powers of x are 10 in both the top and bottom, so this should go to 1/2. We just take the leading coefficients. Okay, so for these guys, it's just looking at it. However, like I just said, it's not always that cut and dry. So for the remainder of this lesson, I'd like to look at some examples like that that don't come out to be as simple. All right, so for the following functions, let's find the limit as x goes to positive infinity and negative infinity. So for this first one, let's say we have the function 4x cubed plus 1 all over 2x cubed plus the square root of 16x to the 6 plus 1. Now, it would be really tempting to just say for either side, right, to just take our leading coefficients, okay, on the top and the bottom. So on the top, of course, that's going to be 4x cubed. Now on the bottom, you might be thinking, well, what in the world do we do with that square root? Well, just take the leading term outside of the square root and inside of the square root. Okay, so we'll have 2x cubed plus the square root of 16 x to the 6th. Okay, now here's where we need to be careful. okay? Here's where we need to be careful, because here's what I think it would be very tempting to do. It'd be very tempting to say that this is 4x cubed plus 2x cubed plus, well, the square root of 16 is 4, and the square root of 6, very tempting to say it's x cubed. Okay, so this would be 4x cubed over 6x cubed. Oh, well, those guys cancel, and that'll just be 2/3. Okay, very tempting to say that. However, if we were to glance at a graph of this function, all right, when we look at a graph, we get two separate horizontal asymptotes. Okay, so if we just graph the 2/3, okay, we see that we only got the right side of the graph. We're missing this -2. Well, what's happening here? And the answer to that question is actually what we did right here. Okay, this step was incorrect. It was almost correct, but incorrect. Oh, okay, how? Well, when we take the square root of an even exponent, we actually get an absolute value coming out. Okay, so let me write that over here, but basically, if you were to say have the square root of x squared, a lot of people will just write that that's x, but that's not true. It's actually the absolute value of x, right? Because if we were to give this, say, if we put 5 in, right? So say we put 5 squared and then took the square root. Well, that's going to be the square root of 25, which will be 5. And if we give this function -5, well, remember, right, that anything squared is going to end up being positive. So once again, we're going to get the square root of 25, which is 5 again. So it turns out that the square root of x squared is the absolute value of x. And it goes even further. If you take the square root of x to any even power, you're going to end up with a absolute value showing up. It's going to be the absolute value of x to that even power divided by 2. So the square root of x to the 6th is going to be the absolute value of x cubed. Okay, the square root of x to the 8th is going to be the absolute value of x to the 4th, which we could actually just write as x to the 4th, right? So when I have an even power, that becomes even when I divide by 2, right? So like 8, you divide it by 2, you get 4. We can drop the absolute value bars because this is always just going to be positive anyway. However, if we end up with that odd power, that absolute value needs to come into play. So remember this, that when you take the square root of x to some even power, the absolute value of x shows up. Okay, so we can now see where we went wrong here, because this 4x cubed over 2x cubed now will, instead of just being 4x cubed, is going to be 4 times the absolute value of x cubed. And where this comes into play is, remember the definition of the absolute value of x? Remember, it's x when x is greater than or equal to 0, and it's going to be -x when x is strictly less than 0. And that's going to be important in these cases because, well, when we go to negative infinity, we're going to be dealing with negative x's, and specifically odd powers of x keep our negatives around, right? They preserve negatives, right? So this is the f we can deal with, okay? So let's break it into two cases now. All right, so here if I have the limit as x goes to positive infinity of 4x cubed over 2x cubed plus 4 absolute value of x cubed, well here, since we're going to positive infinity, x is definitely, well, positive, so the absolute value of x is just going to be x. So this will be the limit as x goes to positive infinity of 4x cubed all over 2x cubed plus 4x cubed. The absolute value is not really going to do anything, so we'll end up with 4x cubed all over 6x cubed, just like we did before, so we'll get 2/3. Okay, so that is from the graph here that we've already seen. All right, so that part doesn't change that much. When we start looking at the negative infinity, though, that's where we'll start to see the change. All right, now that I have this, now that we're looking at the negative side, right, the limit as x goes to negative infinity, since x is going to negative infinity, of course, that means x is negative. And the absolute value of x is negative x when x is negative. So this is going to end up being the limit as x goes to negative infinity of 4x cubed over 2x cubed. Now it would be plus 4, and now I'll replace absolute value of x not with x, but negative x. And remember, negative x cubed preserves the negative sign. So this will be the limit as x goes to negative infinity of 4x cubed all over 2x cubed minus 4x cubed. Right? So limit as x goes to negative infinity of 4x cubed all over 2x cubed minus 4x cubed is going to be negative 2x cubed. The x cubeds cancel, and this comes out to be negative 2. And that's where we get this horizontal asymptote, okay, which I just graphed here as y equals negative 2. Okay, so whenever you see some weird square root stuff showing up, you do need to consider that you're dealing with absolute values whenever you have an even power at the end. Okay, just to show another example of this, when you do the limit as x goes to either plus or minus infinity, that's when you can do the leading term idea. Okay, so this would go to, let me write it like this. This will go to just the square root of x squared over 2x, right? And that's going to go to, remember, the square root of x squared is going to be the absolute value of x over 2x. And now is when we can break it into two pieces, because the limit as x goes to positive infinity of the absolute value of x over 2x, well, remember x is positive, so the absolute value of x is just going to be x, and we'll have x over 2x, the x's cancel, so we get 1/2. However, when we go on the negative side, the limit as x goes to negative infinity of the absolute value of x over 2x, well in this case, x is negative, so the absolute value of x won't just be x, it will now be negative x over 2x. The x's cancel, and we get negative 1/2. Okay, just to show you the graph of this guy here, we can see one horizontal asymptote on one side is 1/2, and another horizontal asymptote on the other side is negative 1/2. Okay. Of course, as I mentioned, it's not always something you have to worry about. because if we look at the limit as x goes to plus or minus infinity of this particular function, 6x squared plus 1 all over the square root of 4x to the 4th plus 3x plus 1. Okay, if we just look at the leading terms, we'll get 6x squared all over the square root of 4x to the 4th. So this would be 6x squared all over 2, and we could say it's the absolute value of x squared, but that's redundant because x squared will just make everything positive anyway. So we can actually drop the absolute value bars when we're left with an even power like this. So this will just come out to be 3, and that will be true on both sides. All right, once again, if we look at the graph, we see that we have a horizontal asymptote. It's the same on both sides. So to the left and the right, we have y equals 3 is our horizontal asymptote. All right, one last example of this type I want to show. And it's a bit of a complicated case, but I do want to show that it is a possibility. Okay, and that's something like this: 1 over 2x to the 4th minus the square root of 4x to the 8th minus 9x to the 4th. If we are looking at the limit as x goes to plus or minus infinity of this, and we do our leading term idea, right, 2x to the 4th minus the square root of 4x to the 8th, okay, that will end up being 1 over 2x to the 4th minus 2 square root of x to the 4th. But again, the 4th power, we can just drop the absolute value bar. And this goes to 1 over 0. Oh, well, we know that 1 over 0 is a plus or minus infinity case. So how do we deal with this? Okay, and my advice on dealing with something like this is if you get something like this that is kind of, you don't like the way it's looking, like we know it's a plus or minus infinity, but like which one is it going to on each side? And, well, let's not forget some of our other algebra techniques. Let's try a conjugating factor here. All right, let's multiply the top and the bottom by this guy here and see what we get. Okay. Remember our conjugating factor, we just change the minus in between to a plus. And the beautiful thing about that is it's going to get rid of all the square root junk in the bottom and just leave us with what's underneath. All right, so now the top is just going to be this, 2x to the 4th plus the square root of 4x to the 8th minus 9x to the 4th, all over. And when we FOIL this out, we're just going to be left with, well, it's the difference of squares, so it'll be a squared. So that will be 4x to the 8th. And maybe I should write this out so you have a better sense of what I'm doing here. This will be 2x to the 4th squared minus the square root of this stuff squared. Okay, the numerator stays the same, but now the denominator is going to become 4x to the 8th minus, and here we just drop the square root. We don't get an absolute value here because what's underneath here has to be positive to begin with, right? So we don't really have to worry about absolute value here. We just already know that whatever happens, this 4x to the 8th minus 9x to the 4th starts off having to be positive based on just the domain of the function itself. Okay, so we're going to get 4x to the 8th minus 4x, well, let me write it like this, minus 4x to the 8th minus 9x to the 4th. All right, so I'm not going to mess with the top. However, on the bottom, when you distribute this negative, okay, the 4x to the 8ths will cancel, and we'll be left with, careful, a positive 9x to the 4th. Okay. And that should probably be good enough for right now, because now if I want to do the limit as x goes to plus or minus infinity of f of x, now I can start looking at the leading terms. Right? The leading terms will be 2x to the 4th plus just the square root of 4x to the 8th all over 9x to the 4th. Okay? And this will become 2x to the 4th. Note, I don't have to put an absolute value because we're ending up with an even power. Okay, so we end up with 4x to the 4th over 9x to the 4th, which ends up being 4/9. Now you may notice that that is not a plus or minus infinity. But remember, when we got that, when we were just looking at the leading terms originally, right? When we were looking at this originally, we just said, oh, okay, that goes to 2x to the 4th minus 2x to the 4th from taking just the leading term. However, this piece is never actually equal to this piece. It's always a little bit less. Okay? So we were missing that when we were just taking the leading terms without, messing with this. So when we changed this from what was essentially a 1 over infinity minus infinity and changed it into an infinity over infinity, which is what we did here. We changed it to an infinity over infinity case. We were actually able to find what the limit was. And if you take a look at the graph, let me zoom in on it, you can see that that's essentially what we get. Okay, we do get the horizontal asymptote at 4/9. All right, the last couple of things I want to talk about are transcendental functions. For example, e to the x, or really anything to the x, say 2 to the x. Well, if x goes to infinity, right, this would be 2 to the infinity. And if you think of 2 to something like 10 billion, that's a huge number. So that'll go to infinity. But as x goes to negative infinity, if you have 2 to the negative infinity, unlike the exponents where that will make that, like exponents as in, sorry, unlike the x to some power, that still gets larger and larger. This, on the other hand, can be rewritten as 1 over 2 to the infinity, which will be 1 over 0. I'm sorry, which will be 1 over infinity, which will be 0. Okay, so the limit as x goes to infinity of, say, e to the x is infinity. The limit as x goes to negative infinity of e to the x is 0. Right, and if you have trouble seeing that, just think, okay, that's e to the negative infinity. That'll be 1 over e to the infinity, which will be 1 over infinity, which will be 0. Okay. The next one would be, say, natural log. Remember, natural log, if e to the x equals y, this is the same thing as saying that the natural log of y is equal to x. Okay, vice versa, if y equals the natural log of x, that's the same thing as saying that e to the y equals x. Okay, so if e to the x goes to infinity as x goes to infinity, okay, well, you could actually take the same idea and sort of flip it around, because if e to the x goes to infinity, that means natural log of infinity is x. But x is going to infinity, right? So actually, the limit as x goes to infinity of the natural log of x is infinity. Okay, now we can't take the limit of natural log as it goes to negative infinity, because it doesn't exist for negative values. Okay, but instead what we can say is it does have an infinite limit at 0. If we approach 0 from the right, we have a vertical asymptote for the natural log. Okay, so here's some graphs detailing that. Here's e to the x. You can see it blows up as x goes to infinity and shrinks down to 0 as x goes to negative infinity. And here's ln of x. Hopefully you've talked about this in your pre-calc class before, but yeah, these operate in this way. Now, of course, trig functions likely don't have any limits at infinity, and most of them don't, because most of them oscillate, right? So sine, cosine, tangent, they all oscillate. Some of them blow up often, but they all oscillate. So the limit as x goes to plus or minus infinity of, say, sine does not exist, right? Because even if you think of the graphs, here's, say, sine and cosine. They just oscillate back and forth between -1. It doesn't matter how far out you go. The limit's never going to exist. Okay, on the other hand, here's tangent, and you can see it oscillates in an exploding way. So tangent has a lot of vertical asymptotes, but no horizontal asymptotes. So its limit does not exist as we go further, and that's going to be true for most trig functions. However, one thing to keep in mind, though, is that the squeeze theorem can still be applied to infinite limits, or limits at infinity. All right, so what do I mean by that? Well, yes, just based on the nature of trig functions, we know that the limit as x goes to infinity of sine of x, for example, does not exist. Right? It oscillates between -1 and 1. Okay, so since it never settles down, its limit's not going to exist. We also can't say it goes to infinity. All right, but what about the limit x goes to infinity of, let's say, sine of x over x, right? Sine of x is trapped between -1 and 1, but 1 over x, right, if we think of it like this, 1 over x is going to go to 0, right? So this oscillates between -1 and 1, but at the same time, this guy goes to 0. Now, I suspect that this thing going to 0 is what's going to take over. All right, so from the squeeze theorem, or trying to set up the squeeze theorem, okay, we always start with what, it's usually easier to start with a trig function, because we know that sine is squeezed between -1 and 1. Okay, And now we can get to sine of x over x by dividing everything by x. All right, so this tells us by the squeeze theorem that the limit as x goes to infinity of negative 1 over x is less than or equal to the limit as x goes to infinity of sine of x over x, okay, which will be less than or equal to the limit as x goes to infinity of 1 over x. Well, these guys, this will be negative 1 over infinity and 1 over infinity. They go to 0. So this implies that the limit as x goes to infinity of sine of x over x is 0. Okay, and if we check the graph, that's what we'll actually see. If we zoom out, we go to a really high value of x, we see that, yeah, this function does oscillate around 0, but does get closer and closer and closer. So if we were to zoom out, there we go, we zoom out, we can see that, yes, we get oscillation, but it gets closer and closer and closer and closer to 0. Okay, so thanks to the squeeze theorem, we're actually able to see that. All right, so for this example, let's say we have the limit as x goes to infinity of cosine of x plus 2 square root x all over square root of x. We can actually use the squeeze theorem here as well, because we know cosine is trapped between negative 1 and 1. So since this is trapped, we don't have to consider it as part of our leading term, right? And specifically, I know that since we're going in the positive direction, right, positive infinity, I know that this thing is always going to be less than or equal to 1 plus 2 times square root x all over square root x. Right, and that is going to be equal to, with just some algebra, 1 over square root x plus 2 root x over root x. The root x's cancel, and this is equal to 1 over the square root of x, okay, plus 2. All right, similarly, right, I know that cosine x is greater than or equal to negative x, right? So we can set up the same exact work here that we did here, except we'll have a minus. Okay, so the function that we're looking at is trapped between negative 1 over square root of x plus 2 and 1 over square root of x plus 2. So if we're taking a limit as x goes to infinity, this is going to go to 0. This is going to go to 0. So we can say that the limit of this thing, right, goes to 2. All right, so I think that's probably enough for now. There are way more examples I can do, but I think this at least shows the majority of the types that you're going to run into. And that should definitely be enough to get you rolling on the homework. So until the next lecture, I will catch you on that one. Cheers.